right, it looks like our liquid is boiling, which is nice. And the temperature has grown up to about 30, which just means this whole apparatus is warming up. We're probably going to see it really shoot up once the boiling liquid starts to condense on the thermometer. Then it'll go up quite substantially. And this is where a lot of times people want to record the temperatures. The temperature we're really interested in is when we start collecting the liquid. So that's the boiling temperature of the material, and that'll help us to identify it. The other thing that oftentimes we'll teach in the lecture, that phase transitions happen at a constant temperature. You might wonder, well, what does that really mean? Now we'll get to see it in action. So I've noticed as I've been talking, the temperature has risen from 30 to 55 as the liquid is starting to condense on the thermometer. Now we're starting to get close to the boiling point of the liquid. When the first drops start to come out into the receiver flask, that's pretty much going to get, hopefully, the boiling temperature of the liquid. And we'll watch. We'll keep heating and keep heating and keep heating and keep heating. And this temperature should not change. If we're distilling one material and it's pure, then as it boils and condenses, it all does it at the same temperature. So that's where we say, like, phase changes happen at a constant temperature. That means as long as this is a pure material, boiling and condensing, it'll stay at that temperature pretty much rock solid throughout the entire distillation. If this temperature starts to go up, there's some higher boiling liquid that's mixing in there or something else. But if it's a pure material distilling properly, you're going to get one temperature through the whole collection. So we verify that usually. There goes our first drop, super exciting, and our second drop. So we've got plenty of heat to start this process going. And I like it when it's going like this. A drop every second or two is a really nice constant distillation rate where we're making progress, but we're not blasting it over with too much heat. So we're definitely going to want to record the temperature now at 66 degrees, it looks like. 66 degrees. And that'll help us to identify the substance. Since we know this is hexane, we already know what the boiling temperature should be, but the boiling temperature is going to depend on the atmospheric pressure. So the atmosphere is pushing down on the liquid, keeping it from forming bubbles. The heat is allowing it to form bubbles, and when there's enough heat to overcome the atmospheric pressure, the bubble can form and escape. So the atmospheric pressure is going to depend on your elevation and the weather and a bunch of other things, but the higher the atmospheric pressure, the higher the boiling temperature. Since we're at about 1,200 feet, we're going to expect a slightly lower boiling temperature than the literature says. So if I'm seeing this boiling, and it is happening right at 66 degrees, this temperature is not moving at all. It's just sitting there right on 66 as drop after drop comes through. So it looks like this is nice pure hexane. It's distilling smoothly and collecting at a nice rate. And it's all at the constant temperature of 66 degrees. Now, if we're at atmospheric pressure, that would be the boiling point, the normal boiling point of hexane. Since our pressure is probably a little different, we're going to look up the boiling point of hexane, compare, and see how much different today's boiling conditions are than the normal boiling conditions. Again, this is something where we want to be attentive, make sure everything's going as it should be, make sure every once in a while check to see if the water is still flowing. These valves tend to shut themselves off a little bit if you try to go with a very low flow, and that's what this one did. This amount of water provides really efficient cooling, so even if the water shuts off for a little bit, it's still going to be cooling here until this water warms up. So we caught it in time and restarted the flow. The dripping is nice and constant here, very smooth. And it looks like we've collected about 3 or 4 mils in here. We started with about 8 milliliters. It'd be nice if we could distill 6 and not too much time. we have 3 hours for the lab, and we're only doing 2 distillations, so we're like way ahead of schedule because we've been careful and got everything set up efficiently, and everything went nice. Again, I'm going to record the temperature about every 20 drops, so we're still at 66 degrees. And it's weird because we're putting so much heat into this, we would expect the temperature to go up, but all the heat is doing is vaporizing the substance and not increasing the temperature, because vaporizing it takes energy. It vaporizes and condenses at the same temperature, 66 degrees right now, and then it condenses over here as well, and that's where we're collecting it. This would be super exciting if this was a new compound that we're going to do research with, or something we were making for a drug company that would sell for $1,000 a drop. We'd be looking and going, whoa, each drop, another 1,000, another 1,000. Since this is hexane, it's still just mesmerizing watching this stuff boil, condense, and drip. But after about 5 or 10 minutes, it's repetitive enough that some people get bored and stop paying attention, which is dangerous. So this is where, if you have a partner, you might switch off, have the other person count the drops and record the temperatures for a little while. And we go about nice 20 drops, check the temperature. I'm expecting it to be 66 degrees, but I want to verify that. If this starts going up, we're starting to get an impurity coming over, and that's when we'd want to stop the distillation, take this stuff as pure, and then not get the higher boiling contaminant in there. So if we have a mixture of liquids, this temperature would not stay constant. It'd change as we continued the distillation, and as some of the higher boiling liquids started to distill over. But it's super beautiful here. We're probably up to about 4 milliliters of liquid in the receiver flask, so we're about half done. Water's flowing nicely. Temperature is still at 66 degrees. This is another opportunity. If you're in a live lab, or if you're sitting at home and thinking about this and questions pop into your mind, that's a great time to take advantage of the resource you have and ask questions, because this is, even though there's nothing really happening here except the smooth distillation, and we're going to pay attention to it, we can be thinking about what's going on, and if we have any questions, we can ask and keep the mental engagement could be high, even though there's pretty much just watching this distill. And if all goes well, we don't have to do much except keep the heat on. Now, as the source flask starts to get low in liquid, that's when I'm going to turn this off and stop it so that it doesn't go to dryness. And I think we're pretty much at that point. It looks like we're still at 66 degrees. And I'm going to turn the heat off so that this doesn't go totally dry. And then we'll let this, as it stops heating. A lot of times, if you really want to stop it quicker, you're going to take it out of the heat by raising the whole apparatus off. Be careful when you do that, because if it says it's boiling at 120 degrees Celsius, that is way above boiling water temperature, so you're not going to want to touch anything that's that hot. So it's good, if I wanted to raise this up, I would touch the clamps, right? Touch the clamps, loosen the clamps, and raise it up that way. And that way I wouldn't be touching any of the hot glassware. So that's something, if I wanted to reduce the heat and stop the boiling here quickly, I'm going to want to get it up out of the heating mantle. Now that the heating mantle electricity is off, this should cool down fairly quickly, but there's enough residual heat in the heating mantle that it might boil for a while. That's like on your stove. I always think of the chemistry as being cooking. If I turn the stove off, the stove is still going to be hot for a while, so I'm not going to want to touch it. I'm not going to want to, I'm not going to expect instantly things to stop cooking. I have to wait till they cool off a little. So that's why before I got totally low in the liquid here, I shut the heat off, raise it out so it can wind down to and stop. This is still bubbling a little as the heat in the flask is still sufficient to keep boiling the liquid a little bit. So It's going to take a little while. It's like after a big exercise, you have a cool down period. After this distillation, we're going to have a little cool down period where things get cooler. The heating mantle gets cooler. The source flask gets cooler. Right now we're at 66 degrees Celsius. And I want to think to myself, is that too hot to touch? What's 66? 37 is body temperature. 40 degrees is a hot summer day. 66 sounds like something I really don't want to touch right now. So we're going to let things cool off before we disassemble. It's like popcorn popping. The bubbles over here are slowing down, but they haven't quite stopped yet. All right, so once this gets to where it's no longer distilling and we're not in danger of having the distillate drip over and come out onto the floor. Actually, I just saw a drop here. So again, it's a little like watching the popcorn. You're not sure when the last drop has come about. But after this cools down, then we're going to want to disassemble this apparatus in the reverse order of the way we assembled it. We're first going to catch our glorious product. So like this guy here, we clamped this flask. We're going to unclamp it. And this is where you want to be very careful, because if you spend a lot of time making this stuff and now we just purified it and identified it, the last thing you want to do is drop this flask and lose all your glorious product. Since it's round, if we just put it on the bench, it's going to fall over. So we're going to probably want a beaker or something to put this in. What I'm going to do right now is just go dump it in the waste, because although this is gloriously purified and we know it all distilled at the same temperature, we're done with it. It served our purpose. And you always want to dump the waste in the appropriate waste container. So in the hood, we have the hazardous waste jar, and it does say on it dichloromethane, acetone, hexane, and butyl chloride. Those are the organic materials that we use in the distillation lab. So go ahead and carefully put that in there. And then cap this loosely, because if any gases form in here on the mixing, we don't want it to build up pressure and explode. And keep this loosely capped, so no pressures will build up. All right, so we've successfully isolated our product. Things are cooling down. We just disassemble this. The condenser we're actually going to use again. So we might go ahead and leave the hoses. And one of the things to pay attention to is if you're using something that's extremely toxic, you might want to be using gloves. This is essentially, hexane is like gasoline. So as you see, a couple of drops of hexane came out of the condenser. They're on the lab bench. They're just going to evaporate, which again, I don't like that, because now I'm going to be breathing hexane, but it's a lot like just breathing a little bit of gas when you fill your gas tank. As long as we minimize our contact there, we'll be okay. This is still pretty warm. Again, the glass stays warm for quite a while, especially in Arizona. I'm disassembling this guy. Be very careful with the thermometer. A little bit of pressure on here could break it, so I lay it down carefully. Make sure nothing gets put on top of this, because that'll snap it like a twig, because it is very much like a twig. And we successfully did not distill to dryness. We have a little bit of liquid here. I'm going to also pour this in the waste, making sure not to dump the stir vane into the waste if possible. So a lot of times we might want to use a magnet to take the stir vane out of the flask. So I have this nice handy retriever tool. I can suck the stir vane out of the flask, and that way I'm not in danger of throwing the stir vane into the waste with the waste. And there goes the waste. Again, some people might say, oh, let's put this back in the hexane bottle, but that's just not the way we do things. And you notice there is a little bit of solid residue in the flask. For whatever reason, there is a little bit of solid, and that actually, I think that might be the silicone grease. So, and that's why I wanted to use a minimum amount of silicone grease, because sometimes it will rinse down and contaminate things. So I think this flask now has a little silicone grease in it. You can see here where it was, when the grease is on there, it's not so cloudy. So over here, the grease did not wash away. Over here, it did. So that's something to pay attention to. Whenever you see something that's a little off color or a little different, think about what the changes might have been. And so silicone grease looks like it gets rinsed a little bit by the hexane. All right, so that's our distillation. It looks like it went super smoothly. We had a couple little things. The water tried to shut itself off. We had to turn it back on. This joint separated at one point when I was assembling the apparatus, but I noticed that and put it back on. So it went super smooth, and I'm pretty happy. Quick and easy, and everything distilled at one temperature. The last thing I would want to do is look up the actual boiling point of hexane, and the sheet's not in front of me, but I think it was 68.5 degrees. We'll have to check that when we review this. But this was distilling at 66. And again, so what that's going to tell us is that today the atmospheric pressure is a little lower, so it's impeding the boiling a little bit, so it's going to boil at a lower temperature. So now if I'm trying to identify an unknown, we have to realize that a real boiling temperature is going to be a little lower than the literature temperature because our pressure is a little lower than atmospheric pressure.